Welcome. Today we cover something crazy. It's called improper integrals, where we integrate over infinite regions like this. Let me just write you down an integral. We integrate from 1 to infinity 1 over x squared dx. And what it means is let me just make a picture here. We have a graph of the function 1 over x squared, which looks more like that. So this is f of x is equal to x to the minus 2. That's another way to write this. And we start at 1 and we compute the area here under the curve. Area all the way to infinity and beyond. So when we do that, we know the antiderivative of this function, right? F of x. We add 1 and divide by that number. So we add 1, we get minus 1. So this is minus x to the minus 1, which is minus 1 over x. And so we can do that. We can fill that in. So minus 1 over x, 1 to infinity, which is, when we put infinity, we get 0, minus 1 over infinity, minus 1 plus 1. And which is equal to 1. So we did here really something crazy. We treated infinity as a number, even though it's not a number, and we got the finite value 1. Let's look at another function. Let's look at this integral from 1 to infinity, and then I take the 1 over the square root of x dx. So let me just draw that also here. So we have the graph looks very much like this. It has also at x equal to 1, it's also 1, but it doesn't go so fast. So it's maybe something like this. So this is the function f of x is equal to the square root of x, which is x to the minus 1 over the square root of it minus 1/2. And then the antiderivative we know, we just add 1 and divide by that 1/2. This is 2 times the square root of x. So again, we are interested in that area here under the curve all the way to infinity. And in this case, what we get is 2 times the square root of x evaluated from 1 to infinity. So we get 2 times the square root of infinity minus 2. Okay, that doesn't exist, so this is infinite. So the limit here does not exist, and this is an integral where we got infinite area. This is an infinite area here. And here, a little bit surprising, we got the finite area. Well, why is it called an improper integral? The reason is because it's improper. I mean, we are not allowed to compute with infinity, etc. And it's so important, it even has been, there's even a journal about it. It's called Improper Integrals. And the current feature has an article about somebody who speaks softly and carries a big bat. Remember, you had been recovered from a shock, and we are doing some trauma recovery today. It was the following problem. So we have again the function 1 over x squared, and we integrate this from minus 1. Let's integrate it from minus 1 to plus 1. Let me just draw this function here. So we are interested in this area here. We have computed this area. And by just computing that integral from minus 1 to 1 over x squared dx, we all know the antiderivative, right? We have minus 1 over x evaluated from minus 1 to 1. If we evaluate it at 1, we get minus 1. So this is minus 1 minus 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 1, it's also minus 1. This is minus 2. So we have seen that. It's an insane example. I mean, this really shocks you if you see that the first time. It has shocked me when I saw that the first time. You know, you would expect, okay, this is improper, right? Because it's improper because we have here a function which is not defined at 0. This is unbounded. There's a pole, there's a discontinuity here at x equal to 0. And so it's definitely not proper here to just integrate through. But you would expect an answer like infinity or something. You would say, okay, that's kind of a infinity. But you get an answer minus 2. And the shock is that it's a negative number. Why do you get a negative number? So let's just see how we do that actually kind of more. We can analyze this properly by just cutting this dangerous part off at first. So let's just do that and start integrating just from t to 1. So let's do that. Instead of going from 0 to 1, we go just from t to 1. So let me just write that, erase this. And then we also have the part here, right, from minus 1 to minus t. So that's another part. So let's just produce the area of this blue region. And that's now perfectly fine because we have no discontinuity here. It's a continuous function. We know we can compute the area. And let's just do that quickly. So we are doing here, we take from minus 1 to minus t, we take 1 over x squared dx, and then we also compute this integral here from t to 1 over x squared dx. So in this case we have a x to the minus 1 minus x to the minus 1 evaluated from minus 1 to minus t plus minus x to the minus 1 evaluated from t to 1. So in this case we get, when we plug in minus t, so we plug in minus t, we get the plus. So this is 1 over t. If you plug in minus 1, the minus 1, and the minus 1 comes here, we get the minus 1. And then here we have the same thing again. So when we plug in 1, we get also minus 1. So minus 1. And when we plug in t, we get, again, with a negative and this minus sign, we get a plus 1 over t. So what we get is, just write this down, we get minus 2 plus 2 over t. And now it kind of makes more sense, and we can recover from our shock, is that we actually have here now an answer which is more sensible. So this is always for t bigger than t smaller than 1. This is always positive here, so this is a positive area. It makes sense. But what happens is when t goes to 0, so the limit t goes to 0 of this area here, minus 2 plus 2 over t, that this doesn't exist. This limit does not exist. It's infinite, and so this whole area is infinite. So what we did when we just took that away here, we kind of brushed over that singularity, and we made something improper. And that's why one has just to be aware of this danger when we integrate over a pole. So this allows also to explain a little bit how we really approach this improper integrals properly. So what we have is we have a solid which has here base. It's a base circle of radius 1, and then the radius goes to 0 like 1 over r. 1 over x. So let's just assume this is the x-axis here, and then the radius is just 1 over x. So this radius is equal to 1 over x. So we do two things. So first of all, we are interested in the volume, of this solid, and we are also then interested in the surface, in the surface area. But we are going all the way to infinity. So we are not stopping at some t here, but we go all the way to infinity. Let's just compute the volume up to t. So the volume up to t so that's the integral. We integrate, and actually here we start at x equal to 1. So x equal to 0 is not part of this. X equal to 1. We start from x equal to 1 to t 1 over, and then we have to get the area here. What is the area? This is something we have discussed last time here. The area A of x is equal to pi r square, which is pi over x square, and then we integrate that pi over x square dx. And we have just done that integral just in section 1. We have seen this is actually just, when we integrate 1 over x square from 1 to t, we have done that and seen that this is equal to pi times 1 minus 1 over t. And now we can take the limit. So if the limit of t goes to infinity of this expression, that is equal to pi. So this trumpet, this is called Gabriel's trumpet. And what we have computed is we have computed the volume. Volume is finite. And what we also can do is we can see what the surface area is. So what we get is, when we look at this is dx also, and then we have, when we unroll it, right, we take that thing, we unroll it. So this part here, just make that also orange. This part here is just, this is dx, and this is, it's a little bit more, but we can approximate it by just, we have 2 pi radius, so 2 pi over x. So what we have is this part here. It's a little bit more, right? This would be just when it would be 90 degrees. It's a little bit more than that. So this is around 2 pi x times dx, and when we integrate that for the surface area, what we get is we can do that also from 1 to t. We can integrate from 1 to t, and then we have 2 pi over x dx. And this is an integral which we also know when we integrate 1 over x. So that's ln, the natural log of x times 2 pi. And then we evaluate it from 1 to t. So this is just 2 pi log of t. Natural log of t. So you know the log function. The log is going to infinity. This goes to infinity for t goes to infinity. This goes to infinity. So this trumpet has infinite surface area. that's why it's a famous problem. So what we have is we have a trumpet which we can fill with paint. We can fill it with paint. So I can take this is 1 liter of paint. This is actually, we have seen that the volume is pi, is less than a gallon. So we can fill it with paint, right? We can fill it with a less than a gallon of paint, but we cannot paint the surface. It's a paradox which you can think about yourself. Okay, let's look at another problem. Let's see how long does the trumpet have to be so that the area, we have seen the area was actually just 2 pi of ln t, the t is the height here, is equal to the area of this tablet here. And we can measure that. It's about 25 centimeters. So this is 25 centimeters times the 17.5, which that's the area. So that's the area A of t. And so if we take that and divide by 2 pi, right, then we get the log of t. So this is equal to log of t. So what we have, in order to get t, we have just to say t is equal to e to the 25 times 17.5 over 2 pi. So 2 pi, what's that? I actually computed that quickly. That's about 69.63. And t is then around 5.2 times 10 to the 29 centimeters. So in order, we start with a trumpet which has 1 centimeter at the bottom, and we want to see how long does it have to become so that it covers this area of this tablet, and we have seen that it's 5.2 times 10 to the 29 centimeters. So what is nice about tablets is also you can look up the size of the universe. In Wikipedia it says that the observable universe has a diameter of 8.8 times 10 to the 26 meters. 8.8 times 10 to the 26 meters. So that's 8.8 times 10 to the 28 centimeters. So our trumpet is 5.2 times 10 to the 29 centimeters. So it doesn't fit. It doesn't fit in our universe. So it's a truly heavenly trumpet, Gabriel's trumpet.